I'm Mercurinis, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's video is a companion to problem number 2, where we calculated the Fibonacci sequence in BF. In that video, we solved the bulk of the actual mathematical problem, but there was still an outstanding bit of code that we didn't go into too much detail on. Specifically, we had a correct result, but we didn't have a good algorithm for printing it to the screen. That video is linked down in the description. I recommend you watch it first. Go ahead, I'll wait. Welcome back. As a brief review, our language of choice was BF. In the language BF, there are 8 commands: left, right, increment, decrement, output, input, loop start, and loop end. We covered most of these in the previous video, but today we'll be focusing on the output instruction. The output instruction in BF takes the value at the current position of the tape and writes it as a byte to the screen. What we want, and what we'll be focusing on today, is the ability to print non-negative numerical values as numbers. For instance, whereas the output instruction will, when given the number 48, print out the character 0, whose ASCII value happens to be 48, we would like to write a program that, when given the input 48, writes the two characters 4 and 8, as one might expect in a more conventional programming language. To that end, we'll be using a code snippet of BF available on the ESOLang wiki. There's no sense reinventing the wheel, but there is great value in studying someone else's wheel design, so we're going to take a look at this code and dissect it. Now, in the last video, I briefly mentioned a rule that's nice to follow in BF whenever possible. Namely, I mentioned that it's ideal to start and end a loop at the same tape position to keep the code as simple as possible. Today, unfortunately, we'll have to throw that rule out. We're going to need to emulate a call stack, running some code several times and storing local values in our makeshift stack. And to do that, we'll need to write a loop whose net effect involves a shift of the tape. We'll get into that more later, but as usual, let's start with a more approachable language. We were working in Ruby for this challenge before, so let's take a look at some more Ruby code. Ruby has a nice command for printing arbitrary values, including integers. So our program looks like this. But that's not terribly illuminating. So let's pretend we don't have that function. In BF, we have a command for printing a single byte to the screen using its ASCII value. In Ruby, the equivalent function is putC, which takes an integer and writes the corresponding single character to output. Before we write our algorithm, we'll also need a plan to implement the modular operator. We discussed the modular operator last week, but as a brief recap, modulo is written in most conventional programming languages using the % sign, and it returns the remainder after dividing two numbers. One nice use for modulo is when writing algorithms that apply to each digit of a number. If we're writing a number n in base 10, the common numerical base most people write numbers in, then n modulo 10 is equal to the final digit of that number. The nearest multiple of 10 below our number n is going to be the tens place of our number, so the remainder after integer division will be the ones place, or the final digit. As a simple example, if we want to sum the digits of a number, we could do something like this. Keep a total count of our sum so far. Then, as long as the current value is bigger than 0, add the final digit of the number to the total, then remove the final digit. Finally, return the total. In Ruby, division between two integers returns an integer. So when we write value divided by 10, this operation will round down to the nearest integer after division. Additionally, the final statement in a function is returned by default. So in Ruby, we don't need to write the keyword return unless we want to exit a function early. Now, our printing algorithm is going to be recursive. We're going to use integer division and the modulo operator to split the number into its final digit and the rest of the number. Then we'll recursively call our function on the rest of the number. And finally, once that's finished, we'll call putC to print out the final digit. Something like this. Every good recursive function needs a base case, and ours is when the value is 0. If the value is 0, do nothing. Otherwise, split the number into its two parts, make the recursive call, and then at the end, print the final digit. Note that we add the magic number 48 to the final digit before printing it. 48 is the ASCII value for the digit 0. And the other digits are conveniently arranged consecutively after it. So by adding 48 to a single digit number, we get the ASCII value of the character representing that number. Now, if you have a good eye for corner cases, you'll notice I said non-negative numerical values earlier. And this function will print nothing if given the number 0. We'll handle the corner case of 0 in a bit, but for the immediate future, let's just assume our number is positive. First, let's get rid of the recursion. If our recursive call was at the very end of the function, we could easily convert it to a while loop using a process called tail call elimination. Compilers do this all the time in order to make recursive functions stackless wherever possible, and to prevent Stack Overflow errors. Unfortunately, our call is not in tail position, so we don't have that luxury. Instead, we're going to use an array to store the numbers we need from our call stack. We'll build up an array of all the digits in the number in one loop, and then we'll iterate over the array using a second loop to print out those digits. First, we create an empty array. Then we iterate until our value hits 0, collecting digits into the array as we go. The double left arrow operator in Ruby can be used to append to the end of an array, so you can think of it as being like append in Python or push in JavaScript. Finally, we iterate over our array in reverse order, printing out each character as we go. It's worth a minor note that this is not how a Ruby programmer would write this, especially the second loop. Ruby, especially its enumerable interface, has a big emphasis on higher order function calls. So if we were writing this in idiomatic Ruby, that second loop would get reduced and would look something more like this. Reverse each iterates an enumerable, such as an array, in reverse order, doing some particular work for each element. In our case, that work is calling the function putC. The enumerable module provides a ton of helper functions like this to capture many common looping patterns. Once you familiarize yourself with these operations, you can often reduce what would be several lines of a for loop into one easy function call. However, in our case, we know we're going to be reducing this to BF soon, so we'll stick to ordinary low-level while loops for the moment. Now, the next part of our computation that we need to unravel is the act of dividing and taking the remainder. As a reminder, BF has only 8 primitive instructions, and none of them are division or modulo, so we'll have to get a bit creative. When we're first taught the concept of multiplication in, I'm going to say probably second grade or so, it's almost invariably introduced as repeated addition. Now, when we get to high school, we realize it can get a bit more complicated than that, and if you utter the words category theory in a mirror, you'll find it can get far more complicated. But for basic integer arithmetic, especially positive integers like we're dealing with, the analogy to repeated addition holds fairly well. Conversely, division, at a basic level, is just repeated subtraction. 32 divided by 6 is asking how many times we can subtract 6 from 32 before we cross 0. So if we're in an environment where we don't know what division is, we can build it back up by subtracting the divisor over and over again until we hit 0. Zooming in a bit, let's write a separate program that, given two numbers, calculates their quotient and remainder using this algorithm. Given two inputs A and B, we repeatedly decrement A until it hits 0. As we do so, we increment the temporary variable mod. Whenever mod hits the value B, we reset it to 0 and increment the div variable instead. At the end, the mod variable will be equal to our remainder, and the div variable will be equal to the quotient, rounded down to the nearest integer. That may be a bit difficult to envision, so let's run through a few steps of the algorithm. Let's say we're trying to divide 32 by 6. At the start of our loop, A is 32, B is 6, and both div and mod start at 0. The first time through our loop, A is decremented to 31, and mod increases to 1. Since mod is not equal to B, our if statement doesn't trigger. The second time through our loop, A is decremented to 30, and mod increases to 2. Again, the if statement doesn't trigger. Then 29 and 3, 28 and 4, 27 and 5. Now at our next iteration, our modulo value hits 6, which is equal to our divisor B. So our if statement triggers, the modulo resets to 0, and div gets incremented. At this point, A is 26, div is 1, and mod is 0. We've removed exactly one instance of the number 6 from our initial dividend of 32. We keep counting down. A decreases to 25, and mod increases to 1. Then 24 and 2, then 23 and 3, then 22 and 4, then 21 and 5. Now we hit the divisor again, setting mod to 0 and div to 2. At this point, A is 20, since we've removed 2 units of 6 from our initial dividend of 32. Fast forwarding a bit, the next time div increments is when A is 14. Then again when A is 8. Then finally when A is 2, div will increment to 5. Then as we approach the end of iteration, A becomes 1 and mod becomes 1. Finally, A becomes 0 and mod becomes 2. Since A is 0, this terminates our loop. The final value of div is 5, and the final value of mod is 2. Now to integrate this into our printing function, here's what we're working with. We'll replace our div and mod calculations something like this. Now, we're going to add one slight modification to make things a bit easier. Recall that in BF, our one looping construct checks whether a variable is equal to 0 or not. Likewise, we build if statements out of loops, so it behooves us to write loops and conditionals in the same way. We'll add a temporary variable called a digit counter. As our current modulo value is counting up to 10, our digit counter will count down from 10, so our inner if statement can simply run when the digit counter hits 0. Finally, remember we have to deal with the corner case of the number 0. We'll add an extra variable to keep track of whether the number is 0 or not. If it is, we'll manually add a single 48 to our digit list. Remember that 48 is the ASCII value of the digit 0, so in this case, the final loop will print the digit 0 one time. Once again, this is written in a bit of an odd order from a Ruby perspective, but this will make the BF easier. Now let's talk about how we're going to store this data on the BF tape. We'll need somewhere to store the single value keeping track of whether our number is 0. This value will start at 1, and will be set to 0 if our main loop runs even once. BF gives us access to an infinite tape of values, indexed by the natural numbers. When we left off in our Project Euler solution, our final answer was stored in register 7. Our intermediate computation had intermittently used registers up to 21. For our calculation, we'd like to use a long stretch of the tape that we're sure is 0. So the first thing we're going to do is move the value in register 7 out to a higher numbered register. That way, our recursive algorithm doesn't accidentally run into something non-zero from an earlier point in the computation. In theory, any register bigger than 21 should suffice, but to be perhaps excessively careful, we'll move our target value to register 40 and start from there. This looks complicated, but it's just some variable shifts, and since we're moving from register 0 to register 40, every time we want to move the tape back and forth, that's 33 characters. So register 40 will store the numerical value we want to store. We'll use register 41 for our is0 variable, and registers 42 and on will be used for our loop. In each iteration of the loop, we're given our current numerical value. In the course of computation, we'll need our digit counter, our final digit, and somewhere to put the rest of our number. As output from the loop, we'll leave behind the final digit and the rest of the number. Now let's consider for the moment that our number is not 0 once again. Then our is0 value in register 41 will be false or 0. Our main loop will, as a net effect, move the pointer one position to the right. As we do so, we'll leave behind a digit of the number and move the remaining number one to the right. We'll repeat this process until all the digits are exhausted. At that point, we'll have a trail of valid ASCII values for the numerical digits on the tape, ending in a 0 value. 0 as a number is not a valid ASCII value for a numerical digit, so the only time 0 will occur is at the very end, sort of like a null terminator in a C-style string. Once that's done, we'll enter our second loop. Our second loop has a net effect at each iteration of moving the pointer one position to the left, printing out whatever it finds there. If it ever hits 0, we know we've hit our null terminator, and we can stop iterating. Now, once again, let's consider the case where our number is 0. We'll start our is0 flag at true unconditionally, and then, if our value is non-zero, we'll set it to false. So if our value is actually 0, the first loop never runs, and the is0 flag is still true. After our first loop, we'll add a check. If this is0 flag is still true, we'll perform our special case. The special case is going to manually rig the call stack to look something like this. Then our second loop can run exactly like it did before. It'll see a C-style null-terminated string whose only character is 48, the character representing the numerical digit 0. Now, let's piece it all together. First, we take our value from register 7 and move it to register 40. Then we set up the places we're going to be storing our values. After this point, register 41 contains the constant number 1, and registers 40 and 42 each contain our desired number. Now, we begin our main loop. If we've hit this point at all, then clearly the value is non-zero, so set our is0 flag in register 41 to false. Then proceed with the loop proper. Initialize our 3 temporary values. Since we're further right on the tape than we've ever been, we can assume everything to the right is 0. So we only really have to initialize the non-zero variable explicitly. The other two come effectively for free. Now we implement our div-mod algorithm to calculate the quotient remainder of our number when divided by 10. This involves some clever tape shuffling, but it really is just the culmination of all the algorithms and placements we've discussed so far. Now we want to take our final digit and add 48 to it. To construct the constant 48, we could simply write the plus character 48 times, and to be honest, that's probably what I would have done, but this particular snippet of code found a clever, shorter way to produce the number by producing 8 and 6, and then multiplying them together. The result is the same, and we effectively add 48 to our digit, and move on to the next iteration of our loop. Now, we write our special case for 0. At the end of our main loop, if the value is non-zero, then our pointer is pointing to 2 values past the end of the digit list. Otherwise, our pointer is left specifically at register 42, which is where it started. So, by moving the pointer 1 to the left, we're now looking at a value which is true if the number was 0 to start with, and false otherwise. If the value was not 0, then we have nothing further to do. If it was, then we write our if statement that rigs the tape to look right for the number 0. This is just placing constants in a few positions, and it uses the 48 trick from earlier to shave a few characters off. Finally, in either the 0 or non-zero case, our pointer is pointing to 1 past the end of the digit list, and the digit list is guaranteed to be terminated on the left by a register with value 0. So we perform one final loop. First, we unconditionally move the pointer left 1. Then, as long as the current value is non-zero, at each iteration we print out the current value, 0 it, and move the pointer to the left. In our particular case, printing the value is the last thing we're going to do, so we don't necessarily have to clean up after ourselves, but it is very nice that this algorithm also zeroes out the registers when it's done. And that's the algorithm. At the end of execution of this algorithm, the number will be printed to the console. If we wanted to, we could force a print of byte 10 to add a new line at the end, but I'm not particularly worried about that at this moment. Here's our printing code. And for the full picture, here it is combined once again with our mathematical solution for problem number 2 in BF. And that, in full, is the solution to Project Euler number 2 in BF. Next week, we'll be back on our usual schedule with problem number 3, which will approach in J, the array-based programming language.